Are we back? So the first paper talk is a recorded talk, and I assume this will just play here whenever things are back up and running. In the meantime, we can discuss a great new project, how to build a hybrid conference software that actually doesn't require you to log into 15 different sites and have 25 different links available. But I think that's early days for this, and hopefully things will get better in the future. I'm sure there's some.
Hello and welcome to our presentation.
Okay, we're good to go.
Understanding the relations between entities such as chemicals, genes, and diseases has been a key aspect in biomedical research. Manual detection of these relations in scientific articles is highly inefficient for MDs. Supervised deep learning can be used for automated detection, but training requires large label datasets. Active learning helps to increase model performance by selecting few targeted samples to label. ML engineers need to examine model performance after labeling. The workflow usually happens in separate platforms, one for labeling, the other for debugging. To tighten the loop between ML engineers and annotators, we created a dashboard to serve them simultaneously. Three main ingredients of our dashboard, namely labeling, active learning, and text data projection, have been implemented in similar tools in the literature. Entity extraction and label suggestions of text data are used in similar tools. We pre-extract the entities and suggest these by bolding and underlining. Active learning and machine learning are combined frequently for different tasks. We offer various models and strategies to be chosen by the user. Finally, to visualize text data, different projection techniques are used in the literature. In our dashboard, we also use selectable projection techniques for visualization and also debugging.
We combine active learning, classification, and dimensionality reduction techniques in the backend with visualizations and annotation capability in the front end. We contribute a workflow that brings the two stakeholders, domain experts and ML experts, together in the same dashboard, each with their own dedicated view and functionalities. Now you will see a demo of our dashboard.
It consists of two modes for the two stakeholders, the label mode for domain experts and the discovery mode for machine learning experts. In each mode, we have 3 pages accessible via scrolling from top to bottom. The right panel of the top page is always a work pipeline of the corresponding mode, with possibility to configure each part of the pipeline by directly clicking on the image. The left part of the top page is the glossary table for technical terms that would appear across the dashboard. Now, the middle and the bottom pages depend on the mode.
We first start with the label mode, which is for domain experts to annotate the data. The middle page of the label mode features the labeling functionality. The annotator interacts with the sentence in the right panel of the label by clicking on two bolded and underlined entities. Once two entities are chosen, a box pops up to ask the user for the label regarding the triplet. Upon annotator's confirmation, the label and the triplet both gets recorded to the backend database. So how are we different from just any labeling dashboard? It is through using active learning to suggest which points are the most important for machine learning model to learn from. The importance of the point is characterized by its acquisition value. The left panel shows the acquisition value plot, where each point corresponds to an entity pair in the sentence in the dataset. The point is sorted by importance from right to left by decreasing the acquisition value. The point in the plot can be browsed one by one by importance using the next button. Once the chosen point in the plot changes, the corresponding sentence on the right panel also changes. Therefore, the annotator can continuously perform efficient labeling by clicking next button and labeling. Rinse and repeat.
So now we proceed to the discovery mode, which is for machine learning experts. Starting with the middle page, we have the two data discovery panels. On the right panel, we have a two-dimensional plot where each point, again, corresponds to an entity pair in a sentence. To transform the text into the point, we first run blue words and get high-dimensional vectors. We then apply dimensional reduction techniques to map the high-dimensional vectors into a two-dimensional vector space. These are the entity pairs already with labels, so we use different colors and symbols for different labels. On the right panel, we have the sentence table along with sentence index and label. One can use the next button and previous buttons to discover sentences in the dataset. Finally, and perhaps more importantly, the bottom page of the Discover mode is for machine learning console. It shows the result of the simulation on how our active learning performs as the labeling process continues. We have the Voronoi plot on the left and the accuracy plot on the right. In the Voronoi plot, the machine learning expert learns about the machine learning model dynamics, how the model's decision looks in the two-dimensional plot. Different modes of the Voronoi plot reveal different information, including where the classifier assigns incorrect labels. The plot changes over time as the annotation goes by. This can be viewed by clicking at the next button. As the button is triggered, the accuracy plot in the right panel gets also updated. It shows how the accuracy evolves as the labeling process according to the active learning strategy goes, compared to randomly choosing entity pairs to label. This gives the insight to machine learning experts to choose and configure which model performs the best.
This is all of our dashboard. We also have the onboarding material for the annotators, which is visible upon first landing or by clicking at the information mark button on the top of the page. For advanced users, the machine learning algorithms can be retrained by triggering the button hidden in the drawer at the hamburger sign.
Now we discuss the results and future work. We observed that active learning only makes slight improvements in selecting the most efficient triplets to annotate. This may be due to several reasons. Models given the amount of data might be insufficient for the given problem, and our coarse-grained simulation where instead of retraining with every annotated triplet, we have retrained with every 25 annotated triplets. Based on the results, we would like to investigate language model fine-tuning and more feature extraction to enhance the performance of active learning. Furthermore, we would like to conduct a use case study. Here, you can see a summary of our work, where we combined several computational tools powered by active learning, visualizations, and annotation capability into a web application. Our tool is designed in a way such that it gives a common communication ground for domain experts and machine learning experts. Thank you for listening.
Hello and welcome to our
Okay. Hey, can you hear me over there on Zoom? Okay, good. We're trying to get you up on the screen in the room. And in the meantime, when you speak, can we hear you? Okay. Okay. Awesome. Okay. Oh no.
There seems to be some feedback.
We cannot hear you. He's muted.
You're muted now.
You can no longer hear me?
Now, yes.
You can hear me?
Yes.
Okay, great. So the question that I have for you is related to your visualizations in your work. Do you think that there is a potential for additional sort of visual representations in the approach that you've taken? I think you have a lot of embedding views and some other types of plots. Do you think that additional work in the future could lead you to something that's maybe more integrative?
Yeah, thanks for the question. That's a good question. And to start off, like I'm Batuhan here, I'm Manuel and Blue. So we think we can investigate other representations as well. Like it doesn't have to be only embeddings mapping into a vector space. But for this, I think we should investigate further future extractions from the sentences. And then based on this, we can maybe have like tree-like structures, which goes in the direction of a little bit linguistics, to understand what the sentence structure will look like and how it affects how things are written in the medical publications.
And yes, additionally, in the future, it would also be planned that we have some user studies. So preferably with some feedback from the users itself, we could also add some further visualizations that would be needed by those end users.
Okay, excellent. Thank you very much for answering this question. There are no questions on Slido. If anyone has a question for the authors, we have a microphone up here, and you are welcome to try this if you have a question. I'm also not sure how much time we're going to start the next video. Say again? You're starting the next one? Okay. Well, I want to thank you again for your presentation and your contribution to this workshop. And we hope you'll have an opportunity to engage with the audience on Discord. And then I would like to launch the next video, the next presentation, paper number 2. Thank you again, and see you. Go for it.
Hello everyone, my name is Carla Florichev, and today I'll be talking about opening access to visual exploration of audiovisual digital biomarkers, an OpenEBM analytics tool. In 2021, the global market value of digital biomarkers was $1.5 billion, and is forecasted to exceed $14 billion by the end of this decade. Digital biomarkers can be defined as objective, quantifiable, physiological, and behavioral measurements that are collected using digital devices. This rising demand of digital biomarkers in clinical research is a result of the growing body of evidence for digital biomarkers to objectively and quantifiably monitor, predict, and diagnose behavior and feelings, clinically translating to disorders and diseases. This unique value to assess behavior and feelings exceeds traditional biomarker constraints and introduces quantitative approaches to diseases and disorders that have been previously limited to qualitative approaches such as self-report and clinical interview-based assessments. Behavioral research in clinical disorders has and will continue to generate excessive amounts of audio and visual recordings. Therefore, the availability of open-source feature extraction toolkits permitting researchers to input these recordings in order to output objective and quantitative datasets is a natural fit. Also, the growing communities of academics in the open-source space are increasing accessibility to subject matter experts in new areas of therapy to explore the potential of digital biomarkers. For example, audiovisual recordings can be inputted into OpenEBM to generate longitudinal and diverse datasets of audiovisual features. However, the novelty of digital biomarkers and their still growing understanding of use when paired with large and complex datasets challenges the exploration of the data. Intuitive and exploratory approaches, such as visualization systems, are not currently integrated into these open-source toolkits. We propose a complementary visual analytics tool to OpenEBM to aid researchers in exploring audiovisual digital biomarker variables. To our knowledge, this is the first visualization tool for audiovisual digital biomarker data. We conducted 5 interviews with domain experts doing research in various biomarker therapeutic areas to better understand how a visualization tool could help in their analysis. Because we encountered so many areas of expertise, we gathered many specific requirements. However, due to time constraints and because we wanted a general solution for multiple workflows, we focused on a subset of requirements that would satisfy all collaborators and the open source communities. Those being, showing details about any subsets of digital biomarker variables available through OpenEBM, visualizing both raw and derived biomarker variables, and emphasizing trends and outliers in the biomarker data. We designed 2 workflows, one for cohort video analysis using the cohort panel, and one for individual video analysis using the individual panel. The cohort panel has three main views: the PCA, the distribution, and the correlation view. Videos are represented by circles. This panel visualizes derived biomarker variables, which are mean values across a video per each variable. In this example, we have a cohort of 95 videos, where an actor is asked to perform one task per video while simulating major depression disorder symptoms. The left query subpanel is used for variable selection for each of the three views. The ID query subpanel highlights videos upon selection. The PCA view provides a cohort 2D grouping overview when considering a subset of biomarker variables. In this example, the videos are grouped by a couple of voice acoustics biomarkers, and let's add a few more to see the results. Looks like most of the videos are grouped towards the lower middle of the view with outliers on the upper extremities. On the right, we have the distribution view that includes one distribution plot for each selected variable. The right part of the plot illustrates cohort variable distributions, while the left part can be used to find individual videos. Let's update this view with the same variables as in the PCA. We can highlight videos from the PCA view in the distribution view and vice versa. It seems that these outliers have low audio intensity. By filtering IDs in the right subpanel, we can hide the unselected videos from the scatter plots for a clear overview. The extra attribute feature colors the videos based on one extra attribute per video, which, in our case, is the task that was performed during each video. This feature shows that the outliers are videos with no audio or those where the actor was instructed to perform a facial expression with no speech. The correlation view uses a matrix to display pairwise correlations between variables. When considering acoustic variables and expressed emotions during videos, we can observe a negative correlation between the audio intensity and contempt, while sadness and surprise seem to be positively correlated with this variable. The individual panel is used for one video analysis. This panel has 5 main views: the head sketch, the facial, movement, acoustics, and the correlation views. The panel visualizes raw longitudinal biomarkers for the video that is selected from the lower left ID query subpanel. OpenDBM outputs raw data variables for 3 biomarker categories, those being facial, movement, and acoustics. The corresponding views for these biomarkers show temporal plots for each selected variable. In this example, for facial activity, sadness seems to be detected alongside fear and anger. The placement of the views helps in finding patterns between biomarkers. The head sketch view is used for facial and movement biomarker analysis. 4 masks can be applied on the face to show mean values for facial asymmetry, pain expressivity, face expressivity, and action unit intensity values. Action units are measurements that show how particular facial features change when someone shows an emotion. By selecting one of the available emotions, we highlight the action units that get triggered for that emotion. Hovering over the face will show the action units numbers and their placement on the face. In this example, sadness seems to be detected. Finally, we have a head movement mask that shows how much the head moved in each direction. A timeline at the top of the screen splits the temporal data into 20 timeframes. When changing the time point, its corresponding timeframe is highlighted in the temporal plots with red, while the mean values for the face and head masks are updated for that timeframe. This helps in better making connections between biomarkers. Because video and audio are extracted at different frequencies, we also display the data file's actual frames at the top. Lastly, a correlation matrix shows interrelationships between longitudinal variables. We evaluated our system with 3 domain experts using 2 case studies. For more information about the evaluation, please check the paper. The general feedback was very encouraging, people saying they wish they had this type of tool earlier. The evaluation generated a lot of interesting ideas, which we hope to tackle in our future work. In conclusion, we presented what, to our knowledge, is the first visual analytics tool for audiovisual digital biomarkers made for and made available through open source. We presented the cohort panel, which is used for analyzing cohort-derived biomarker variables, and the individual panel used for single video raw biomarker variable analysis. We evaluated the system using 2 case studies, and we hope that our work generated intersection points for the open source community to contribute. Thank you for your attention. Hello everyone, my name is Carla Florichel, and today I'll be talking about opening access to visual exploration.
Here at a second time. Thank you, Clara, excellent. I can see you here. I'm going to turn my video on so you can see me too, and maybe we're going to get it up there on the screen. So great presentation. I see there are questions here on Slido. I'm going to get started with the first one, and that is, in which medical domains do you see the biggest uptake of OpenDBM?
Yeah, that's a great question. It's such a fascinating field. Right now, one of the biggest application areas of novice researchers to get involved in digital biomarkers is neurodegenerative disorders and psychiatric disorders. So anything regarding how you're feeling and turning that to clinical translation. So turning those qualitative assessments to quantitative is a big push in those fields.
Great, thank you. Another question here regarding your work is if you could comment on the implementation of the interface.
Sure. We try to create something that's pretty simple to use, and something as general as possible, because there are so many there's so much behavioral research, so many disorders and diseases to be tested using OpenDBM. So we wanted something that can incorporate all this data, something very useful and easy. But our future work should include something more specific to each disease or disorder. So,
I'll just add that right now, what we're trying to do is give tools for researchers to ask any questions they want to. So the generic application was for the purpose of someone dealing with child autism to look at any issues with specific faith markers versus somebody looking at what would be called therapeutic alliance or shared decision making, seeing if there's a synchronicity between the therapist and the patients being talked to. Very different use cases. So we want to open it up so that they can ask more specific questions and then iterate on the interface for more specificity.
Wonderful. Thank you so much. I'm not sure, we're a little bit over time already. So I will ask half of a question from Slido, and that is, how do you ensure that the biomarkers in OpenDBM are actually properly validated before you make them available to other researchers?
Such a great question, and that's the whole mission behind this project. It's really an open science initiative. We're trying to give people the tools, innovators, the real intellectuals, putting them into contact with these tools to validate these that are already available. So this is a centralized platform, and we're trying to say, look at these tools that are available for you to use today, but we would like you to validate them as a community. So that's kind of what we're building. That's what that's the spirit of this project.
Wonderful. Thank you so much for the Q&A and for your great presentation. With that, I want to wrap up the first paper session. Thank the presenters again. And with that, we'll have a 25-minute break. We'll be back here or on YouTube or anywhere else at 10:45 a.m. See you later.